So just to recap very briefly, so we went from tokenization to um, representing words as by some number, by some numbers using one or TF, IDF, etc. Then we went on to find some kind of a syntactical meaning through CBOW and skipgram. That was also not very effective. So we went to a global vectorization using GloVe, and though we could find some syntax, it was not sufficient. So then after GloVe, the basic problem was we were missing um, morphological understanding. So for morphological understanding, we took the discussion to uh, fast text. And fast text, we got morphological understanding of the words, but then we now are at a junction where we do not understand the polysemies. So right now, what is my situation is that I'm able to represent a word effectively uh, using a vector. And the thing is that if I have a word like uh, today, it represents this as a vector, and it understands the words around this particular word, and that effectively tells it what is the context in which this word is being utilized. So that much we have achieved. And also we've achieved things like if I have a word like walk and walking, so I understand that this is essentially the same word, and I'm able to represent it appropriately so that it doesn't confuse between the two words and does not take these two words as separate. In fact, it finds out that this is just an addition, so it will represent it as a hash ing, and so that's how the morphology is understood. Now the problem comes with words like, let's say, bank, which I can utilize in different contexts. So sometimes it's a financial institution, sometimes it's a geographical feature. If I have a single representation of this, then I am not able to decide, I'm not able to decode in what sense I'm using the word bank. So I have to find a way so that it is dynamic, it is not static like the way we have right now. So I should typically have two different representations of the same word bank. So one representation will be when I'm using it as a financial institution, and one representation should be when I'm using it as a geographical feature. So this is what we will try to achieve today. And for this, or the technology which we will discuss is the technology called ELMo. So it is um, so this will allow us to move from static representations to dynamic representations. So let's go ahead. So as usual, I will walk you through the complete neural network setup. How exactly we will set up the neural network, then we will train the neural network, and we will end the session by applying it on a practical problem. We will which we will demonstrate whether it actually is working or not. Okay. Good evening, Aditi. I just saw you joined in.
Hi, Partha. Sorry for joining late. I'm at a bad network area today.
No problem. Okay. So this is where we are. So what do you call? We have a single word like a bank, and instead of representing as a static representation, we will try to make a what do you call dynamic representation so that it understands whether I'm in a financial institution or whether I'm a river bank. So before I will come back to this presentation once again at the end of the show. Before that, let us go to the neural network and set up the neural network and understand how we create the neural network. Right? Any questions so far? Anything from the past sessions also you have a doubt?
So just one question. So looking at this diagram, I think looks like, okay, if we have to classify financial, we take help of some words like deposit, credit.
Mm-hmm.
So which is potentially indicating it is a segment of financial element, and something like a river or turn or something like that, like, okay, that is indicating the river side of it. So just thinking like, okay, do we also have a possibility like, okay, let's say a word like flow. So flow could fall under financial segment, and flow also could fall under river segment. So if it all like, okay, something comes middle of the junction, so uh, how does it's basically been treated? Like, okay, do we have any such possibilities?
Yeah,
Just
the thing
thinking.
is that, see, the entire, by now you have understood that it is not understanding meaning of any of the words. Though we are
Correct.
very away, it is not understanding meaning of any of the words, right? It is basically making a context of the word based on the surrounding words which it has got. Okay. So when we put in the corpus, from the corpus it will pick out all the different areas where it is utilized, and it will analyze what is around it. So if flow happens to be around other words like river or something like that, then it will take it as a geographical indicator.
Got it, sir. Right.
Okay, because see, you must be very clear. Though I'm trying very hard, but I'm not able to teach him any kind of meaning. I'm only teaching him some kind of mechanism by which he can get a context. That's about it. Nothing more, nothing less.
Understood, sir. Thank you.
Yeah. See, the word bank is very critical because it is not only used in geographical indicator or a financial institute, because I can also use bank in the context of let's say the banking on a road that I do at the turns when we raise or lower the road slide, and that is also banking. So there are many cases like this where the word bank can be used. Right, and there are many words in English or any other
Also
language.
storage.
Yeah, yeah. Power bank, like you have, right? So there are so many contexts. There are many words like this, which now the entire thing is that I can decipher all the different contexts of the word bank, but only to the extent that what are the words surrounding it. So only that much it can utilize to understand the different context in which the same word is being utilized. Right?
Got it, sir.
Okay. Let us.
But
Yeah.
before we move on, so I
Yeah.
had one question. See, in the initial classes, we talked about tokens like BP, sentence pieces, and then word pieces, right? So none of that tokenization mechanism used so far in all the embeddings that we are creating, because I see that we are all looking at the word-based tokenization, and at least in the fast text, we split the word into multiple pieces, right? So why are we not looking at a BPE or for tokenization here to create the vocabulary and then train on that? Any reason why we are doing that?
Yeah. Actually, what do you call fasttext was the first technology that we discussed where we use subword tokenization. Okay. Now, the BPE is something which was developed specifically by OpenAI for ChatGPT, for GPT actually. So when we the class after next, when we conclude the word embeddings, we will conclude with utilizing BPE. Okay, and similarly, sentence piece is the tokenization technique utilized by Google when it generated the technology called BERT. So when I discuss BERT in the week after next, we will use sentence piece tokenization, and what do you call? We will see its application. So right now, all these technologies they were developed prior to both GPT and BERT development. So they are basically utilizing the word-based tokenization technique only.
Okay. Like the classic old algorithms that were already implemented, and then the BP organization came after this. Okay.
Yeah. But the thing is that I tried to impress upon you last time that though you may say that this is a legacy, but this is not really legacy because for example, I shared with you that skipgram model is heavily utilized by modern companies like Spotify or Alibaba, and so these technologies still have a big place in our space. Not everything that we can achieve with more modern technologies like BERT or BART or GPT can be achieved. Can achieve what older technologies like skipgram or ELMo and things like that can achieve. Okay, so that's why it is important that we do not forget them. And in fact, I'm building upon these basically to impress that how the journey goes. Now, the same technology, the same building, what we have done, we will be utilizing it further during the transformer development. Now the thing is that you can say I could have very easily started the transformer and said, okay, fine, use BP or sentence piece and provide the embeddings. But that is not the whole thing. If you are really engineering, and in the very first session, I showed you that there are instances where, in spite of BP being a very superior tokenization technique, it produces an inferior tokenization as compared to word tokenization. Right? That was the first thing which I demonstrated to you in the first class of our series. So if that is the case, if you analyze the corpus and find that we are getting a bigger benefit by doing a word tokenization, should we not go ahead with word tokenization rather than going for just because it's advanced, just go that then we utilize BP? What is your opinion as an engineer?
So yeah, so I would probably, as you mentioned, I would try to implement the BP and see what are the pros and cons, what is the word, and based on the algorithm or the model that I'm trying to develop, what is the model's requirement is what I'll try to use, rather than just being the latest. If my model is asking for a word-based tokenization, then I would stick to word-based tokenization. That would be my approach, Patra.
Exactly. That is even I would what do you call profess for that. So it is not that just because I have a more modern technology I should utilize it. I should have awareness of what is all available to me in my hand, and I will analyze my data. That is the way of doing any kind of machine learning project. That first we collect the data. We first of all find out what are the questions to answer. Based on the questions to answer, we figure out what data to collect. After we figure out what data to collect, we collect the data from the sources that we have identified. Once the data has come in, then we analyze the data, and we analyze it, and we do the descriptive analytics of the data. And then from the descriptive analytics, then we decide what kind of technology to utilize for modeling. So that should be your approach, not just that I got the data, so now let me apply the most modern technology, and that would be a wrong way of going ahead. Would you agree?
Understood. Yes, I do agree. Yes. Yeah.
Okay. Any other questions coming to your mind? Anyone?
Not from me. Thanks.
Okay. So now let's make the ELMo architecture. You'll notice that it's quite intense, and things are getting really complex here right now. So let me start by loading the libraries. I've done that. I make my sentence. So now you see that I have done a word level tokenization here, and then I build a character vocabulary. Character vocabulary means this is coming from fast text. It is an extension of fast text. Fast text also, if you remember, we did a character vocabulary, and then we assimilated the characters into the different words, right? So here I find out the unique characters that I have. After I done my character vocabulary, I formulate my words out of the characters. So now my largest word is deposited. It has got some 9 characters, and these are basically the identifiers, the character IDs. So here I have these characters. So each of them have got an ID which I have provided. So this is the character ID which I have provided based on the tokens, and then each word is formed out of the character IDs of equal length. I have to have it of equal length, so I have taken the length as that of the largest word. right? So this is clear. Any questions here?
Partha, while you're identifying characters, the small I and the capital I is also considered. So that means that in this ELMo, we are not worried about the uppercase, lowercase issues. So we consider, we have to consider both the uppercase as well as lowercase.
Yeah, they are separate characters. See, the thing is that it goes by the ASCII numbers. It doesn't understand this and this are the same, right?
Okay.
If I was conscious about that, I would have probably made everything lowercase or made everything uppercase. But right now, I'm not conscious about that. I want the natural flow to happen. So as far as the machine is concerned, these are ASCII numbers. So ASCII numbers for this and this are different. So they are two different characters.
So, which means that in the ELMo case, we don't have to worry about any pre-processing of the data.
No,
With
no,
lowercase.
no. That is absolutely not required.
Tata, what about when numbers are present in the database?
Numbers are also ASCII characters. So they will also have their own ASCII numbers. So they will become a unique character for them for that.
Okay, yeah. Thanks.
Okay. I could change. See if I make it like this. Okay. I changed it. So now I have, let's see, what are the tokens? So I get these as the tokens. This is correct, right? So if I make my character list now, you see this 1, 2, 3 becomes different characters, right? And then if I make my
Yes, and also the special characters are taken into consideration.
Yeah.
Okay.
Yeah. Okay. So 1 minute. Something is gone in. Yeah. Okay. Now if I convert them, so it becomes like this. So now we have more number of words tokens in our list. So we have got everything, and so this is a representation. Now I have made a class in which I have implemented the ELMo neural network. Let me explain this little bit to you guys. So what I do is that I find the character embeddings based on I already made vectors out of each word. So this I will make the character embeddings based on that, and the padding is 0. That's what I have done. Now in the ELMo we have a 3-layer neural network. The first layer, what I'm doing is that I'm making a CNN, a convolutional neural network. Why I'm making convolutional neural network is because in the what I will do is supposing I have a word like this, walk, then I will this is my word. So I will make you know that in CNN I have to make a filter. So I will, let me say I make a filter of 2 characters. This is just an illustration. I make a filter of 2 characters. In this I put 2 characters, that is E and D, right? Then what I will do is that I will put this filter on top of my word. So I will put this filter here and I will put ED here, and I will check. I will do a convolution with this first 2 characters. Do you? It will see that these are totally different. So it will signal that these are not the same. Then I will move this filter forward. So I will move this filter on this position, E D here, and now I will do the convolution with this and with this. So again, I find that ED is not this. Supposing that the word is walk, so then I will move the filter further forward. Then this is like ED here, and then I will do the convolution with L and K. Again, I find it is not there. So then I will move the filter forward here. Okay. Then I will do the convolution with this and this. Again, I find that it is not matching. Lastly, I will put the filter here. And I will, when I convolve with this, then I find that the signal says that ED is present in this. So now, the moment I find this, what will this convolution give me if I convolve like this? It will give me that ED is present, and this filter is for finding what do you call past tense. Okay, so this filter is for finding past tense. Then if I find that ED is present in the word which I am convolving on, then I know that this particular word is a word in the past tense, which is talking about the past tense. So like this, I will make many filters. Maybe I will make a filter for ED, I will make a filter for ing, I'll make a filter for so many different things. So if I do this, what is happening is that at the end of all the convolutions, I will know what is the exact characteristics of the words in my corpus. Did you get the idea? Silence.
Yeah.
So, remember what I'm doing in convolution. Supposing I have a picture like this, and I want to figure out where is the nose and where is the eyes. So I will make many filters. So one filter is just for finding the nose. One filter is just for finding the eyes. One filter is just for finding the lips. And then I will put the filter here and I will move the filter in this direction first up to when I reach here. Then I will go like this. So then I will find out, okay, this area contains the nose. That is how I find in convolutional neural network, right? Is that idea clear to you?
Yes, Partha.
Okay. That's what I'm doing. Now, this is on a two-dimensional, if it's an image. And when I'm dealing with a word, when I'm dealing with sentences or words or language, it's a one-dimensional convolution. That's about it. So the first layer, what I do is that I create a convolutional neural network. After the convolutional neural network, I found out all the characteristics. You see that this is how the neural network should function. What I've shown you, that it should figure out by himself what are the features. So it is finding out the features. Oh, past tense. It is past participle. What do you call past continuous and things like that. So everything it is figuring out by himself. And I'm not going to be defining to him. Okay, fine. Look for ed, look for ing, etc. He will go through the corpus under his scanner and he will figure out what kind of filters he should look for. So that is all going to happen by itself. So that's why the CNN is there. Okay, after the CNN, then what I will do is that I will make a LSTM. LSTM is basically a recurrent neural network. In the recurrent neural network, what it will do is that it will go past my corpus in a forward direction first, and it will remember. Okay, fine. And this is a bidirectional LSTM, by the way. Bidirectional LSTM. So it will go in the forward direction. It will figure out what is the relationship between different words. You know that in LSTM it can remember. I have a memory, right? I have a memory, so I remember what came before me, what came after me, and everything. So I go in the forward direction. I remember what came before me at this point of time, and then after I finish that, then I will go in the backward direction. So I also know that what came after me, right? So first of all I understood what are the different features, and then I find out how the features are what do you call connecting with each other, right? So this gives me the complete idea regarding how my what do you call corpus is structured around each individual words. Now what I do is that in the first pass, first LSTM, I found out something regarding the relationship between words. Then what I do is that I do a second LSTM also. I go even more deeper. So maybe the first LSTM found out the syntactical meaning of the words in the context in which they are utilized, and the second LSTM I find out the semantic meaning. So this is where I'm finding the semantic meaning. So the total network becomes, I first do a CNN. After the embedding, of course, I first do a CNN and I pass the CNN to a LSTM, and then I get the output of the LSTM, and then again I put it into a second LSTM. This is my neural network. Okay, of course I will do some more steps here, which I will tell you. So
Partha, I'm sorry to interrupt. I'm not
Yeah.
able to raise my hand or from phone.
Yeah.
But my question is that CNN and LSTM both in themselves are neural networks, right? So they must have multiple layers within itself, at least the CNN, not LSTM.
No, both have multiple layers. Both have multiple layers. You see here, what you see the network here. First of all, see in CNN, I'm having kernel, right? The kernel has got a size, and I told you I will have multiple filters. So you see, I'm defining here. I will have multiple filters. It is not a single filter, right? So it will this.
Okay, understood. Yeah.
This is number one. Second thing is that LSTM also I'm telling that you have more, you have a, what do you call, hidden layer, which is got different sizes, which is got different. So number of hidden layers, I'm not fixing it. I am defining it so that I can have multiple number of hidden layers. So this is also a deep neural network by itself. Same here also. Okay.
Okay, got it, Partha. Thank you.
I will show you the network so you would be understanding. Yes, Eknath.
Sir, conceptually, I understood what you're trying to say. LSTM is also like, okay, a long-term memory, short-term memory that we would like to identify and probably like, okay, a bit of a context or correlation that we wanted to do. But since one LSTM itself is a bidirectional, and think like, okay, our corpus is also like, okay, probably like, okay, extensively long or whatever it is like, okay, so the two LSTM that we repeat like, okay, the same LSTM process like twice. I was not able to understand very clearly why we are repeating twice, kind
Yeah.
of a thing.
Okay. The thing is that they're not the same LSTM. You see here, the first LSTM, the input is coming from the CNN. Okay, look at this. The input is coming from the CNN. The
Sure.
second LSTM, the input is coming as the output of the last LSTM.
Oh, okay.
So they're not the same. So what I'm doing here is that the first LSTM, I'm finding the syntactical meaning of the words. I'm finding the syntax. Okay. The second LSTM, what I'm doing is that I'm utilizing it to find the semantics. Okay. So
Right. So
they've got different purposes.
I understood. Like, okay, so in this like, okay, approach, if my corpus happen to be significantly large enough, will still like this approach will be able to deal with such large corpus
Yeah,
also?
it is a very deep neural network. So it will obviously require a lot of resources and time to train a large corpus with this architecture. But
Sure.
our goal is that we have to make a technically capable system which serves our purpose, and for that we will have to arrange required resources.
Got it, sir. I'm clear. Thank you.
Partha, the code for both the LSTM looks the same here. Is there like, are we defining it somewhere else? Whether what is the first one doing and what is the second one doing?
Yeah, I will show you. I will show you that.
Okay.
The LSTM definition will remain the same, but you see they are all are variables, and these variables will carry different values. That is why the LSTMs will be different.
Sure.
Okay, now see here, I'm making the forward pass. In the forward pass, what I'm doing is that first of all, I'm passing the embeddings. Embeddings, I showed you that I'm doing the character embedding, which I have already showed you. After having done the embeddings, I pass the embeddings into the CNN, and the CNN will produce the output, which I discussed with you already. After doing that, what I do is that I get a token representation from the CNN, and that token representation I take it, and that will become the input for the LSTM. Right? I will get some token representation at this stage, which I will put it into LSTM. Now this LSTM, it will produce output, and this output I will give it to the next LSTM, and after the next LSTM produces the output, I will normalize it and do a softmax to get the probability regarding which are the most likely context for each given word which I have, and then I will project it. That will become the final normalized weights for me. Okay, actually, this is more intense. This is simplified version. So after the CNN, what I will do is that I will do a max pooling here. Max pooling because I am using multiple filters, right? I'm using multiple filters, so I cannot consider multiple filters to be my output. So I will do a max pooling. Max pooling basically I will find out which filter has got the maximum influence. So if I do a max pooling, I will get the filter with the maximum influence. I will take that one only. And then after having figured out the max pooling, then what I will do is that the data will become all over the place. So I will do a normalization, a batch normalization. Batch normalization will scale it back to a standard range, each data point. Similarly, after doing the LSTM, I will do a batch normalization so that I get the data in standard range, and same I do it in second LSTM also. That is the complete network, but right now I'm just doing the forward pass, so I've kept it simple. Okay, so now let me run this, and now let me create my network. So this is, I just rub it so that it's visible clearly. Just 1 minute. Okay. Now you see that this is the convolutional neural network. It has got a kernel size of 3, and it has got 16 filters. Okay, and so 16 filters will give 16 outputs, and then it will putting it into a LSTM of 12 units. So this will give 12 units. So this 12 units will become the input, and then 12 plus 12 become 24. So I will get a 24 element representation of the words at the end of the show. So let me confirm it by showing it to you. So forward pass is completed. Now you see here the ultimate. I've got 24 element output in the final embedding, right? So let me show you the output so that you understand. So this is the thing, and yeah, so the token representation is 16 here, and this is after the CNN 16 filters, and then I go to the LSTM1. It will give you 12, no 24, and this becomes the output, and the final LSTM also will return it at 24. So now I'm getting embeddings. So you're seeing that I'm getting embeddings for the words. Now the thing is that whether the embeddings are really able to figure out polysemy or not, that is to be ensured, which we will figure out after the complete training. So now let me see the final embeddings, what I have got. So I've got the embeddings for all the words, and I've got 24 element representation of each word. So each embedding contains 24 elements, right? Now what I do is that I take a particular token called bang, and I find out what its embeddings are. So this is the embeddings, and that's how. So if I check the neural network, so it is like this. So I put the character embeddings, and I put the input. I was the character embeddings. Then I got the CNN. Then I got the max pooling. After max pooling, I did a LSTM1. I did a LSTM2, and ultimately I did a weighted sum, and I got the final ELMo embeddings. That is 24 characters. So that is just the network we have set up. So is this part clear? If it is clear, then we can move on to training the network.
Yes, sir.
Yes,
Everyone?
Doctor.
Yeah, sure. Okay. So now that we have set up the network, we know that we got a CNN and 2 layers of LSTM. Now let's build the complete neural network training. So neural network training, I start by getting the thing. And now you see here, intentionally what I've done is that I have kept 3 sentences. One sentence is, I deposited money at the bank, I withdrew money from the bank, and the fisherman sat at the bank of the river. Now, why this is done intentionally is because you notice that these 2 sentences are containing the bank in the financial institution context, whereas this is a geographical indicator context. So now these 2 representations should show me a bank in financial institution context, and this one should be different. So let's see whether it can do that or not. Okay. Any comments? You want to add something?
What is toy corpus, Partha?
This is a toy corpus. This is not a
Achha,
real corpus.
we are calling this a toy corpus. Okay.
Okay. Okay, now I build the word vocabulary. So all the words I have taken unique words. Then I build the character vocabulary. So now I have got all the unique characters. So I find the max length. I found the max length. Then I can create the these are utilities. So I create the tensors. So these are all nine element tensors. I'm not showing the things because I've shown you already. So now I make the ELMo model same as before. And now I will create the model. Model is created. So we have a CNN followed by LSTM. Convolution is basically CNN, LSTM, and then a linear output. And now this is just the training setup, the hyperparameters for training. And now I do the training. Okay, so it does a training. Okay, training is over. Now let me see the loss curve. So it has learned something, definitely. But learning happened very quickly. Now I see the weights. So it has got these weights. That is not important. Now let's come to the all important thing. That is what are the embeddings and whether it is able to decipher things correctly or not. So I got 3 embeddings. So this, I'm interested in the embedding for bank because that is my focus area. So I got some embedding for the bank. Now look at the first thing. This is the first sentence in which I got embedding for the word bank. Now this is the second sentence. Notice, is the embedding for the word bank in the first sentence and second sentence the same?
Yes. Yeah.
No. Check properly.
No.
They're not the same.
Minus 0.498.
Yeah.
Yeah,
498
minus 0.58.
458.
Okay, my mistake. Sorry.
Yeah. Now, is our first goal achieved that I'm getting dynamic embeddings for each word?
Yes, sir.
Yes or no?
Yes, yeah.
Right? You notice here that the bank here is even more different. Correct? Notice this. So, am I getting dynamic embedding? Is my first requirement is served?
Yes, sir.
Yes.
Now let us analyze the embeddings. Okay, I take out the word bank in all the 3 different sentences. They happen to be in the same place. Now let me do a comparison of all the embeddings of the bank. So now you notice that, okay, I do a comparison here. Notice this. Between sentence 1 and sentence 2, the distance between the word bank is this much. And the cosine similarity is this much. What does this cosine similarity tell you? It is 0.9998. That means they are almost similar to each other.
Yes.
Correct?
Correct.
Between sentence 1 and sentence 3, the distance is much larger. Sentence 3, I was river bank. Sentence 1 was financial bank. The distance is much larger. Do you notice that?
Yes.
And also the cosine similarity has come down, 0.998, just 9998. So this is a little bit dissimilar as compared to these 2 banks. Yes or no?
Yeah,
Yes, sir.
slightly less, yes.
Yeah, because this is a very small corpus. That's why you're seeing that they are not these are not falling very far apart. But it is very clear that between sentence 1 and sentence 3 and sentence 2 and sentence 3, the distance between the two bank embeddings are much larger as compared to sentence 1 and sentence 2. Do you notice that?
Yes, sir.
Yes, yes, partner.
So it has been able to decipher that the bank in sentence 1 and sentence 2 is used in almost the same context, but in sentence 3 it is used in a different context. Can I conclude that?
Yes, I'm still not convinced about cosine similarity because it is very similar, but distance wise, yes.
Yes. Then cosine similarity, yeah, I told you it's a very small corpus. That's why it is not able to make out that much. But it is another thing is that cosine similarity is not running away to a very far place. So that means to say that it recognizes that this is the same word, right? It recognizes the fact that it's the same word, but it still says that the contexts are different. That is what it has achieved.
Yeah, right, partner.
So Partha, in this case, should we assume, should we consider both similarity, cosine similarity, as also the distance to differentiate? Okay, even though the words are same, the distance is saying it is far away, so which means that the meaning could be different or semantic could be different.
Yes, that is how it is understanding. That is how the model is understanding. Okay. So this was convincing for you guys?
Yes.
Yes,
Yeah.
Papa.
Yes, sir. So just I was thinking like we compared. Okay, sorry, 1 and 2 is also fine. No, all good, sir. Thank you. It is convincing.
Okay. Okay. So now let us put this into application, and then let us see how it works. So let us. So what I've done is that I have taken the. Oh, this was got disconnected. Let me just reinstall the libraries. Just give it a little bit of time. Okay, done. Now I restart. What I'll do is that I will take news from Reuters and then I will give it some input. It has to be able to figure out the news items based on the input. And the input what I will give is not exactly what the news item contains. I don't even know what the news item contains. I will give it some input and it has to figure out the news item which is closest to the input what I provide. It will be able to do that only if it understands contextually what are the meanings of the words. So I downloaded some news from Reuters. So this is the Reuters news, which is this is static thing, but I will show you dynamic thing also. Now I define some categories. These are you see completely arbitrary. I can change it also. So I do this and I prepare my documents. Okay, there are 6,000 documents. Now I'm taking a model. This is based on ELMo. I'm not building ELMo here afresh. I'm taking a ELMo model which is already available, and I'm going to utilize the embeddings from that model. So now I just write some utility functions. This is not important. So I got my embeddings. The embeddings are of the size 768. Okay. I also define a function for cosine similarity just for comparison purpose. Not just for comparison, this will be the basis on which it will find the similarities. Okay. Just 1 minute. Okay, so all the embeddings are created, cosine similarity is created. Now I define a search function And then now you see that I'm giving queries absolutely arbitrarily. Now I have no idea regarding what is included inside the news items which I have retrieved. Right. So let me make the queries and see what result it gives. Now let's analyze this. So my query was oil production and food prices. It found 3 news items. So you see that it says this. Does it seem like this was for oil related news?
Yes, sir.
Okay.
Yes, Papa. Yeah.
Now this one seems like tons corn. Now this is slightly off. Um, but it is related to production, but this is not a very good fetch what it has made, right? And this one again is a good fetch. It has understood the context and it has made a good fetch. Don't you think so?
Correct.
Right. Let's see the next one: foreign exchange and market pressure. So this news item seems, now you notice that it is not doing a word by word match. Do you notice that it is doing a context match?
Yes, sir. Got it.
This is a good result what we have got here. All 3 items are very appropriate. Don't you think so?
Yes, sir.
Okay.
Yes, Papa. Yeah.
Now look at this grain export demand. So Bangladesh passes soft wheat, it's grain. Egypt on corn, US exporter on corn. This is also good. The interest rate, this is Freddie Mac, this is all this Freddie Mac, etc. These are all Bank of France. These are all relating to interest rates only. These are all a good fetch. So you got the idea how it is able to make a contextual understanding of the words.
Yes, sir.
Semantically also, now we have achieved semantic similarities also.
Yes, Papa. Yeah.
Okay, I think I made a tool. Let me just show you. Gemini. This one, yeah, it is come. Gemini. What happened? Why is it not working? Yeah, it's working. And this is the one. So let us look at it. Hmm. This is live. That was on a data set which was there, but this is working on live data set. So you can, I will show you how it can search, do context search here. Just 1 minute.
In the meanwhile, Partha, why we started with the character level tokenization in this model?
No, why did we do that? Because in fast text we established that we have to go for subword, right? So that we have the morphology understanding.
Yes.
That is why we continued with that.
No, but that there we still were going with at least a combination of 2 or 3 words. Here we were just we were doing like character level single word, single
Yeah,
character. Sorry.
yeah, because I want to figure out the words which are similar. That I can only do if I do a character level tokenization, right? The morphological understanding, like running, I should be able to make out that they are the same word. So we made the progress last week. We should not lose on that progress, right?
Okay. Yeah.
This takes a little while. Now it's loading the model. So just 1 minute. Yeah, now it's ready. What happened? It's taking some time to load. Just 1 minute. Yeah, it is loading. It is fetching the Reuters news. That is why it is taking time. Not Reuters, RSH. It's taking a lot of time. Okay. Now tell me a topic which you would like to fetch news about. Any topic.
US-Iran conflict.
USA? What? USA?
Iran conflict. USA-Iran conflict.
No, Iran. It's Iran conflict. Okay. I say search. So it should find me news items which is appropriate for this particular search topic. It's doing something. Hopefully it will get good results. You can also try at your end while my machine also may be slow. I'm not sure. Okay, let us see. The topic is this: it found 100 fields, and then is it? So this first one is stalemate in a continuous. Is it correct? What do you think?
Yes, Partha.
Worked?
Yes.
Yes, sir.
So you guys are convinced about it?
Yes, sir.
Okay.
Never had the doubt, Partha.
Thank you. So we build a model. Now it is able to what do you call make dynamic embeddings and it is able to understand. So just this recap. So our purpose was that to differentiate the same word having two different meanings, two different contexts or more. So we built, and first of all, we were having static representations, and we found a mechanism to make dynamic representations. And it was a fixed word ID. Now we go in by characters so that we can also take care of morphology. And we used the context in both ways. So far, all the neural networks that we had made, if you remember, we were not using a bidirectional, any kind of bidirectional neural network. The first time we introduced a bidirectional so that we understand going forward and going backward, what would be the context in which the word is utilized. And we made two LSTMs because one was for syntactic finding and one was for semantic finding. So this was the 3 layers what we made. So first we found the syntax, and then we found the semantics, right? Sorry. So this is what we did: 16 convolutional layers, and it discovered different aspects of the words by itself: prefixes, suffixes, roots, all these things. But I found out by convolutional neural network, and then, like I told you, I made a max pooling so that I get the most significant aspect of the words into my embeddings, not everything. And then I made a LSTM's forward pass, and in which I'm finding the context, first the syntax, and then the semantics by the layer 3, and then so this is my complete neural network. Ultimately I get my contextual embeddings. Okay, so we saw that we are able to distinguish this, and we made the embeddings. They were basically the different. We saw the numbers; they were different, so they are not the same, right? So it was able to distinguish, and it was able to make out difference. And we found the distance, though very small, because the corpus was small, but it nevertheless there was a distance and there was an angle between the different things, and they were different for when I'm using in the same context, they're much closer. When I'm using in a different context, they are slightly further off. This also I demonstrated to you guys. Right. Then lastly, we made the Reuters model in which we put in all the news items, and then we made a search, and it was able to search semantically. Right. So any questions at this point of time?
Not so much.
Anyone? Any questions?
No, so this was awesome, actually.
Okay.
Apart from the searching, it's like contextual matching and searching. Any other use cases part of this ELMo can be used?
Not really. Not really that we can use it in any other use cases, right?
Okay.
Because right now I've only reached the stage where I'm having some semantic understanding of the words, so I cannot apply it anywhere else at this point of time. Okay. So
Okay.
now coming to your question, like how do I broaden my horizon? That we will do in the next class. Now, what I have done right now is that I have been able to find the semantic meaning of the words by going forward and backward, right? Both forward direction and backward direction. Now, what I should do is that I should not only look at the forward direction and backward direction, but I should look at what are the specific words which have higher impact on the meaning of the word I'm looking for. Like for the bank, the word instead of the word deposited or withdraw. These words have higher amount of contextual meaning as far as the word bank is concerned, or a fisherman, that has got a higher amount of contextual meaning. Now I should be able to find out which words have got the higher amount of contextual meaning, and then interpret the word in those high dimensional contexts. So that is our next step, where I will introduce you for the first time to the huge concept called attention mechanism. Now, actually, you may know historically that there was a Google employee, Indian by the way, who wrote a paper called "Attention is All You Need," and that single paper catapulted itself into the formulation of the complete LLM that we have today. That one single paper. So right now, we must next week. What I will do is that I will introduce you to the attention mechanism, and this is one of the central points of the LLM architecture. And while I will show you how the attention mechanism was used in the first application at Google called BERT. Right? So that is our context for next week. So I hope you will join in, and we will have a good discussion. Right?
Yes. Partha, if you can still take it, I have two small questions.
Yeah.
One is, are there any practical places or practical applications where they are using the ELMo? And a second, like the Google search, when we do it, it is also doing some kind of a similar thing, right? And it has nothing to do with. First of all, okay, let me rephrase the question. Google search also does similar things. So, is it also can we think of ELMo as similar to a Google search?
Yes, it is. It is. Actually, it is the same. Nothing different. You notice
Okay, I
that
see.
you notice that I could have used ELMo also in the Google search, but I will use BERT, which is a slightly superior thing, because apart from just paying attention to just the direction in which the word is utilized, I will pay attention to the individual words which have the highest contextual meaning in that in the setting which I will make. So Google actually utilizes BERT in their search engine.
Okay, got it. Yeah. So most of the search engines more or less use the same kind of algorithm.
Yes.
Okay, got it. Thank you.
Okay. So let me just share all the material for today's class so that you can refer and take advantage.